Okay, welcome everybody and thank you for coming today. My name is Ricardo Vinuesa. I'm an associate professor at KTH in Stockholm. And today I'm gonna tell you more about our work on using deep neural networks to model temporal sequences in turbulent flows. In particular, we want to understand a little bit more of the temporal behavior. So to do this, and I want to highlight that the funding is by the European Research Council and the Swedish Research Council, what we do is that we try to take a model for a turbulent flow. This is basically a low-order representation of the near-world region of turbulence. This is a model by Moelis and others, where what they did was to come up with a 9-mode representation of the flow, which is actually very convenient for us because that allows us to produce massive amounts of data at a very low computational cost and to try different neural network architectures to be able to try to model the temporal dynamics. So what we do is that we start from an initial base condition. The spatial modes are fixed and they represent streaks, vortices, and interactions among the elements in the near-world region, and we're going to try to predict the temporal coefficients associated with these spatial modes. What we will do to produce many different data sets is to perturb the initial conditions, so the initial values of these 9 coefficients. In particular, we will fix 8 of them and only perturb the 4th coefficient. So that will allow us to really create massive amounts of data that will help us to train and to evaluate the performance of our deep learning models. So this is basically what the data looks like when we are integrating in time this 9 equation model. So here you can see the temporal evolution of the 9 coefficients, starting from the first mode. An interesting thing is when the first mode takes a value of 1, which is constant, all the other modes go to 0, and that's essentially the case where you have relaminarization. In our data set, we're going to avoid relaminarization because we want to focus on the turbulence part of the flow, essentially. And that's what the flow looks like. So here you can see a frontal view where you can actually observe the high and low speed streaks and also the lift-up effect together with the stringwise vortices. Again, this is a quite good model of the near-world region of turbulence. And on the second figure, what you can actually see is the span-wise movement of these streaks. So essentially, this corresponds to some of the manifestations that you can observe in the near-world region of turbulence. I want to highlight that everything from this section is published in Physical Review Fluids. You can see the reference here. This is work initiated by Prem Srinivasan, and all the data and codes are available online, so you can find everything to reproduce all the results that I will be talking about today. So let's start by talking a little bit about neural networks. What I'm showing you here is what we call a multi-layer perceptron. It's the simplest type of neural network architecture where all the neurons of one layer are connected with all the neurons of the next one. So in this case, we will have an input vector, chi, that you can see here, and the output vector, zeta, that you can see here. We want to take all the input information, and you would have a number of hidden layers in between, which will allow us to improve the predictive capacity of our neural network. And in our output, we will have 9 coefficients, because we want to predict the values of the 9 temporal coefficients in the next step. The key here is that multi-layer perceptrons, like the one that we can see in this case, are not able to exploit the temporal dependencies in the data. That's because all the input data is introduced, as you can see over here, as an array of data points. It doesn't matter if the data corresponds to this step or the previous one or 10 steps before. All of them are input points, and then we're applying all these operations through the hidden layers to obtain 9 inputs. So we may end up with actually a very, very large number of parameters in my input layer. In particular, we will have 9 p parameters in this first layer. 9 because we have 9 coefficients, and p is the number of steps that we use to make our predictions. So what happens when we zoom in into a network? No? If we take one neuron of this architecture and we try to take a magnifying glass and see what happens inside, what we can see is that basically this reduces to matrix vector multiplications plus something else. So most of it is linear algebra. And when we are trying to train a neural network, what we are doing is through backpropagation, trying to adjust these parameters here. This is what we call the weight matrix, and this is the bias. So you can see that the operation in the neuron is just the multiplication of a matrix and a vector and the addition of the bias, which is another vector. And the only thing that differentiates this from linear algebra is that after this matrix vector multiplication, we apply a nonlinear activation function. If this nonlinear activation function wasn't there, then it wouldn't matter to have a very deep network or a very shallow one, because everything could be reduced to just basic linear algebra operations. But having this nonlinearity that is introduced by this activation function, we can really significantly improve the predictive capabilities of our model, especially when we make it deeper and deeper, because of this concatenated application of these operations. And the other interesting thing is that we can, in principle, model any smooth function with any complexity due to the nonlinearities that are introduced by this activation function. So in this example, I'm showing you a sigmoid, which is a quite popular activation function, but there are many others. The hyperbolic tangent is another possibility. And in computer vision, if you remember some of the videos that we talked about before, a very popular activation function is the rectified linear unit. So all these ingredients are basically what allows us to make the predictions. And remember that the whole point is that we want to train an architecture, which means to find the weight matrix and the biases of each of the layers of our neural network. So what does it mean to train a neural network? Well, essentially, you are showing the neural network a number of examples. In this case, these are labeled examples. So this is a supervised learning scenario where we have the inputs, which is a vector, a very long vector with the values of the 9 coefficients in different steps. And we want to see the output, which would be the value of the 9 coefficients at the next step. So it's labeled. And we are first training our architecture in such a way that we are showing what the input corresponds to what output. So this is what we call the training stage. In the training stage, what you can see here in this orange line is that we find a loss, which in this case we define it as the mean square error between the true data and the predicted one. And what we do is that we are going through a number of epochs. An epoch is a pass through the whole training dataset. So as we might expect, the loss, the error that we make in our prediction, goes down as I increase the number of epochs, as I am going forward with my training. And the second line that I am showing over here in kind of blue is what we call the validation loss. And the validation loss consists of evaluating the model that I have trained on data that has not been seen during the training process. That's very important. This is to be able to ensure that the network is able to generalize beyond the examples that have been shown during the training process. If everything goes well, typically the validation loss is a bit higher than the training one because the data has not been seen, but typically it should also go down, in such a way that you are able to progressively improve the performance both in the training and the validation datasets. What could happen? Well, sometimes things don't go perfectly. One possibility is what we call underfitting. And in underfitting, the problem would be that this blue curve will be very, very high. And also the training curve will be quite high. The situation here is that we are not having enough parameters in our neural network to be able to fit all the complexity of the data that we're trying to predict. And in this case, what we should do is probably increase the capacity of the network. So increase the number of parameters that we have in our neural network so that the errors generally go down. Another possible problem during the training process is what we call the overfitting. And in the overfitting, what happens, and this is illustrated in this panel over here, is that the training loss goes down progressively. So I actually perform better and better in the data that I have seen during the training process. But the validation, which is this blue curve over here, that one goes down for a while, and after some time it goes up again. So there is one point after which adding more data essentially produces more error. And the reason for this is the fact that the network has become so good at the training data that it's not able to generalize to new data. And it actually performs worse on new unseen data. And typically what happens with this is that we're probably having way too many parameters for the amount of data that we have. So essentially we are having a fit that is adjusting too well the training data that we have in our database, and that's not allowing us to generalize. So one possible solution for this could be to increase the size of the training dataset. In that sense, for the size of the network that we have, this architecture will be able to generalize better, and hopefully we'll be able to predict in a more reasonable manner in unseen data. This also gives us an indication of a typical strategy when training neural networks, and is what we call the early stopping. So what could happen is that for a while, the validation loss gets quite low, actually, much lower than this, and then it starts to increase. And one possible strategy is to stop training at the point where the validation loss is quite low. So this is something that is also quite common in deep learning, and is what we call the early stopping criteria. So armed with this, we use our multi-layer perceptron, this fully connected architecture, to be able to make some predictions. And what we realize in an architecture which has 3 hidden layers, 19 neurons per layer, and actually a very, very large number of steps to make our predictions, is that we could get reasonable results, but not excellent results. So we are using 500 time steps to be able to predict the next time step. And because we have 9 coefficients, that's a total of 4,500 values to only predict 9. That seems a bit like an overkill, and again, I want to highlight that the reason for this is that the multi-layer perceptron cannot exploit the temporal dependencies in the data to improve the predictions. But what you can see here in the instantaneous flow visualizations is that the flow looks okay. I mean, you see the high and low speed streaks, you see the vortices, but when you see the span-wise movement of those streaks, there is some information missing. There is some discrepancy between this instantaneous visualization and the reference that I showed before. Therefore, if we look at the statistics, if we look at the mean behavior of the flow, what we can actually do is define a norm, basically an integrated relative error that compares for the profiles, for the statistical profiles, the true data and the predicted data. And we evaluate this norm for the mean profile, the string-wise velocity fluctuations, and the Reynolds shear stress. So we calculate these quantities. The level of error that you can observe here, well, I mean, it's a reasonable prediction, but we can see that particularly in the velocity fluctuation case, the errors are still quite high. No? So this can certainly be improved, and clearly there is some discrepancy when we are looking at the values of the peaks in the fluctuations. Now, we played a little bit with this architecture. We tried to increase the number of hidden layers. We played with the number of neurons. Turns out that we can get a bit better results. So we can actually get, with this architecture, MLP4, only 18% error in the fluctuations and around 3% error in the mean, which means that our predictions are, reasonable, but still that's something that can be improved. And the key here is to be able to exploit, as I mentioned before, the temporal information in the data. So to do this, we're going to consider this other architecture. This is what we call a recurrent neural network. These are very popular for predicting temporal sequences, because in recurrent neural networks, we are precisely able to exploit the temporal information in the data. So essentially, when we introduce the input, and the input is over here, so this would be the values of the 9 coefficients at the present step and then the past ones, the network is able to understand the temporal connections between these data points. So it's actually able to understand the temporal dynamics and make predictions based on that. This is something that would be exploited when making the prediction of the next time step, which would be over here. And the key ingredient is essentially this recurrent connection. So in this recurrent connection, what you can see is that the output that we have, so this is basically my information in this step, it goes over here. The output of this step goes connected to the input of the next step. And in addition to that, the information from the first layer is connected directly with information of the first layer at the next step. So these two things, this recurrent connection and these arrows over here, which give me information directly from the previous step into the current one for each of the layers, this is something that allows us to really understand those temporal dependencies. More information of this can be found in this article, the one that I mentioned before, and also a more recent article by Jamireza Ibasi and collaborators. This is in the International Journal of Heat and Fluid Flow, and again, you can check all the data and all the codes online. Okay? I will provide all the links so you can access this. So these recurrent neural networks exploit those recurrent connections. They have only one problem, and it's the problem of the vanishing gradients. So essentially, when you're starting to use quite old information, when you start to backpropagate in time, what happens is that the gradient, so basically the variation of the data that we use to be able to do the learning, that gets progressively smaller. So at some point, you don't have any data to be able to train. You cannot really exploit the past information because it doesn't give you any meaningful information to be able to train your neural network. But luckily, that is solved through a very popular architecture. This is the so-called LSTM network, so long short-term memory architecture, which relies on a very smart gating mechanism to be able to solve this vanishing gradient problem. So the LSTM architecture, which is very widely used in many applications, for example, on your phone, when you are writing a message, the autocomplete functions are usually relying on these LSTM networks. So if the autocomplete doesn't write what you want it to write, you need more training. It's the fault of the LSTM network. And the idea is that if you zoom in into these units that you have in the LSTM, you also have weights and biases. So you also have the type of parameters that you will have in a multi-layer perceptron. However, the architecture is a bit more complicated. You don't only have one weight and one bias, you have this sort of algorithm which relies on different gates. So these gates, we have the forget gate, we have the input gate, and the output gate. They work together in such a way that we can filter out how much of the past information is important now and how much of the present information is important to make the next prediction. So essentially, we have a bunch of weights and bias terms for these gates. So the number of parameters of an LSTM is higher than that of a multi-layer perceptron. And through the training process, you can actually get a pretty efficient way of predicting the temporal dependencies on the flow. So this is a comparison of the performance. If we take the results from the MLP and we train it on the same number of data sets that we have with the LSTM, we can reduce the errors from 3% in the mean and 18% in the fluctuation to something actually much better, as you can see over here. And if we increase the amount of training data, we can actually come up with less than 0.5% error in the mean and only 2.5% error in the fluctuations. So we can get really good results when trying to incorporate the information of the temporal dependencies of the data. Making a bigger network has the potential to improve the results, but at some point, having a too large network and increasing the number of steps that you are using to make your predictions may lead to worse performance. And that's because at some point you want to be able to balance how much of the instantaneous predictions you want to get perfect and how much of the long-term statistical behavior you want to get perfect. So there is a little bit of a trade-off there, and I'm going to be discussing some of the implications of having good short-term predictions compared with the statistical ones. But before, let's look at the data. I mean, clearly, as I mentioned before, the relative errors are very low for the mean and the fluctuations. The statistics are in excellent agreement, and even the instantaneous visualization resemble the near-world region behavior that we would expect, with the streaks and the vortices plus their interactions in the near-world region. Even if we look at more complicated statistical quantities, we're looking at the skewness, the flatness, we are looking at the vorticity fluctuations, we can actually get excellent predictions with the LSTM network by being able to exploit this spatial and basically this temporal information that we have in our data. Now, one caveat to everything that I've said so far. The statistical performance is really good, so we are able to predict the statistics, the long-term behavior, pretty well. If we look at the errors in the instantaneous predictions, so if I'm trying to look at the prediction of the next step, the errors are a bit higher. 13% error in the first coefficient, and the rest of coefficients, they have similar error levels. If you compare here the truth and the prediction of these temporal coefficients, what you can actually see is that the data deviates, but what is interesting is that the behavior is kind of similar. When you have a burst, so a very large value of the coefficient, the prediction will also have a very large value of the coefficient. Maybe not at exactly the same place, but it will resemble the same dynamical behavior. What does that mean? Well, what we can do is try to compare the dynamical properties of the learned system, the neural network, with those of the original set of ODEs, of ordinary differential equations. Let's keep in mind that this reduced order model of the near world region of turbulence, this is a chaotic system, which means that a very small perturbation of this chaotic system will take it to a different trajectory. And when you are training with these neural networks, well, we are having very, very good predictions, but we are making a very small error on the order of 10 to the minus 6, 10 to the minus 9 of the value of the coefficient, but not 0. Which means that we might be actually capturing the dynamics of the system, but going towards a different trajectory. And to assess that, we compare, in this case, the Poincaré map of the first and third coefficients by ensuring that the second coefficient is equal to 0 and negative temporal derivative. What I'm superimposing here is the Poincaré map from the original set of ODEs and from the LSTM architecture. And what you can see is that the interaction between the first and third modes, which is captured by this Poincaré map, is in excellent agreement in the two configurations, both in the ODE system and in the neural network, which means that we are having pretty good predictions from a dynamical point of view. Even more, something that one can do to try to study the dynamical behavior of my system is to perturb it. So we can introduce a perturbation on all the 9 modes. So this is basically a norm of the deviation between the trajectories measured on the 9 modes. And I can actually introduce a very small perturbation of 10 to the minus 6, which is basically of the order of the level of error that you could expect from our neural network. And we did that with the original system of ODEs. So what we do in this figure is that we're measuring the deviation with respect to the original trajectory as a function of time for the original data, the reference data, and for the LSTM with the same perturbation. And what we see is that we have the vertical axis is a logarithmic scale, which means that this linear trend is actually an exponential growth. We see an exponential deviation with respect to the original trajectory, which saturates at some point, and then, well, essentially we are living in another trajectory with a certain deviation with respect to the original one. What is interesting is that the slope of this curve, of this line over here, which is actually given by this exponential that you can see over here, is what we call the Lyapunov exponent, or the leading Lyapunov exponent in this case, which is measuring the speed at which we deviate with respect to the original trajectory. And in both cases is the same, is identical. So what this shows is that by perturbing the original dynamical system with an amplitude equal to the very small error that we have in our neural network, we obtain the same deviation. In other words, we have been able to learn the dynamics of the system, and the reason why we observe deviations of the temporal coefficients is because of the chaotic nature of the data itself. So we are actually able to completely understand the chaotic nature and the dynamic behavior of this particular data set, which is fulfilling because at the end of the day, it means that we are doing something reasonable. A couple of additional examples before concluding. What I showed you before was that near world model of Moelis and other, which is essentially a 9 equation representation of the near world region. That model lacks one thing, and is the multi-scale character of turbulence. So what we did was to take a minimal channel. So we just constrained the domain size to basically simplify the dynamics of the flow, and do the same thing. We applied proper orthogonal decomposition to the flow in this minimal channel, and we tried to predict the temporal dependencies of the coefficients from those POD modes. This is work by Borrelli and others, also in the International Journal of Heat and Fluid Flow. So you can see all the data and all the information over here. What we observe in this case is that in the minimal channel, there is a quite broad range of scales, of temporal scales, on those POD modes that we obtain, because this is turbulence. The key is the LSTM doesn't perform very well if we want to capture all the temporal dependencies of all the scales at once. But what one can do is group the modes into different ranges of scales and train different LSTM models for each of those ranges. And then the agreement that we found between the reference and the predictions for the minimal channel was very similar to the one that we obtained with the Moelis model. So actually, what we are showing here is that the LSTM is very good at predicting turbulent flows over a range of frequencies. So if you want to model the whole multi-scale characteristics of turbulence, maybe the LSTM could be a bit limited. This takes us to the last example of today, where perhaps there are ways of trying to account for the multi-scale character of turbulence. This is an article that we worked on recently. It's published in the Journal of Fluid Mechanics, and you can see also the full reference here with all the codes and all the data. We are using a transformer architecture to model the temporal dependencies of turbulence. In particular, we use it to produce an inflow generator for a turbulence simulation. And for the purpose of modeling the temporal dynamics, I want to highlight that transformers are based on the attention mechanisms. And then this attention-based approach, what it does is that it's finding parts of the temporal series that are of high relevance for the next prediction, essentially. And of course, this doesn't mean that the regions of high relevance, of high connection between each other, have to be sequential. The LSTM is sequential, so if important information is way in the past, it will probably be lost. It will probably not be accounted for through the gating mechanisms. But transformers have a longer memory in time. So the idea is that the multi-scale character, where large scales are much more it takes more time, that's much slower than the smaller scales. That information is going to be way in the past, and smaller scales are going to be closer to each other. The attention mechanisms that characterize transformers are going to be able to properly account for this multi-scale characteristic of turbulence, and therefore that allows us to really predict the temporal dependencies in turbulence pretty accurately, outperforming even what we could do with the LSTM. So have a look at this, and I really believe that transformers have great potential for turbulent flow predictions precisely because of the multi-scale character that can be quite nicely captured by these neural networks. And this is all for today. I wanted to highlight the temporal predictions that we can do in turbulence with deep learning. And I want to acknowledge everyone who made this video possible, including the KTH Visualization Studio, the KTH Digitalization Platform, InfraVis, and all the funding agencies for my research. Thank you very much, and come for more in the next video.